So today we're going to talk a little bit about theorems that are what I call a duh theorem. So there's something that you've already known, you're already processing these, but we're formalizing them with some actual formal language. The first one is the mean value theorem. So let's think about a graph. If I'm looking at any graph and there are 2 points that have the same y value, if it's not a constant function or a flat line, we can assume that to get from point A to point B, you've had to have a max or a min. And in calculus, that means that the derivative is 0. So if I have the same y value on an interval, somewhere, if it's not a constant, there's a max or min. So what the mean value theorem and the Rolle's theorem are going to start implying is behaviors that we already know with the graph. They're logical behaviors. We're just formalizing them. So what Rolle's theorem is going to tell us, if we're continuous, I have y values that are equal and we're differentiable, there's 1 point where the derivative equals 0. So that's going to be Rolle's. Now, we have to be careful. It has to be differentiable. So these two graphs are an example of a situation where I don't have a place where the derivative is 0, but it's because it's not differentiable. So you're going to have to check that differentiability. So before you apply the theorem, make sure it's continuous, make sure it's differentiable. This is an example with Rolle's theorem where there are 2 points where the derivative is 0. So that's why if you look at the formal wording of the theorem, it says at least 1, okay? So it doesn't tell us there is 1, it tells us there is at least 1. So now we're going to look at the mean value theorem in much the same light. The mean value theorem is going to say if I have a secant line, and I find the slope of that secant line, I'm going to be able to make some assumptions about the actual values. So if I look at the mean value theorem, if my function is continuous and differentiable, then there is at least 1 point on the graph where the derivative equals the slope of a secant line. So here we have this green secant line, and we're told that we have this point x, f of x, and if I look at the slope of my secant line, it's going to equal the tangent line that would be here, or the derivative. So you're probably thinking, how am I going to apply this? Right now, it's common sense. We're just trying to make sense of what is happening on a graph and why a graph behaves like it does, okay? So we're really just working on making sense. Now, again, we have that wording, then there is at least 1 point. Here's an example where my secant line slope is 5, and my derivative slopes are 5, and there are 2 points. We're really just looking to know there's at least 1, at least. Oops, there we go. This again, we're formalizing what we already know. The derivative of any number is 0. So what this is saying is if the graph is at 0 for all points, then I know my original function was constant, meaning it was just a number. We know this. We're just formalizing it. If I have functions where the derivatives differ by a constant, then I know that I have functions with equal derivatives can differ by a constant. So if I have the derivative of x squared versus 2x squared, I could have a difference of 2 because of that 2 in front. We already know this. We're just formalizing the language. Again, intervals of increase and decrease. You already learned this. If the derivative is positive, it's increasing from the first derivative test. If it's less than 0, it's negative and it's decreasing. So this is formalizing what you already learned in the first derivative test. So really 4.6 was formalizing things we've already seen, we've already probably taken note of within our notes, but we're just giving it a formal rule to happen.